This is Module 9. We're doing Example 2. This example comes from the Tintle textbook section 3.1, which you should be sure to read as well. So the question here, the research question we're trying to understand is, can dogs sniff out cancer? A dog sniffs 5 bags that contain human breath within each bag. One of those 5 bags contains the breath of someone who has cancer. The dog correctly identified that bag from the cancer patient 30 out of 33 times. It says here that we're going to use alpha equals 0.05 to test our null hypothesis. Remember, alpha stands for the significance level. We're going to decide if our p-value is smaller than alpha. If our p-value is smaller than alpha, we'll reject the null hypothesis. All right, so the null hypothesis here would be, our first guess might be that the dog is guessing. If the dog were guessing about which bag the cancer patient's breath is in, then since there's 1 out of 5 bags that has that breath, he would get it right approximately 1/5 of the time in the long run. So pi would equal 0.2. And if the dog is not guessing, the alternative hypothesis would say that pi is not 0.2. Dog is not guessing. He would be doing either better than guessing, so pi would be bigger than 0.2, or worse than guessing, pi would be less than 0.2. Okay, it turns out then we saw that our sample statistic, we observed the dog getting it right 30 times out of 33, so our sample statistic is 0.91. Now I have skipped some steps here, but just recall what would happen then. We would build a null distribution. The null distribution would be centered at 0.2. It would show us the distribution of sample statistics. It would show us the sample statistics we expect to get if it's true that the dog was just guessing. We would then locate our sample statistic p-hat on that distribution and identify the p-value. Turns out when we do this, our value of p-hat of 0.91 is way up here in the right tail. And it turns out the p-value is 0 when we did the simulation. The probability of getting a sample like ours or more extreme is 0. So in that case, we would reject the null hypothesis because our p-value is small. We have strong evidence against the null. And in fact, because our p-value is smaller than alpha, we reject the null. So our overall contextual conclusion would be that we have strong enough evidence to say that the dog is not getting it right 20% of the time in the long run, but we still really haven't answered our research question. All we've said here is that it doesn't seem like he's getting it right 20% of the time, but we still don't know what pi is. What percentage of the time is the dog getting it right in the long run? It seems like it's not 20%. So I'm going to go up here, I'm going to cross that off. So the next thing you might do out in the real world is actually make another null hypothesis. You might then say, okay, well, it's not 20%, and that makes sense because we saw the dog get it right 91% of the time. How about we make our null hypothesis value of the parameter higher? Maybe the dog's getting it right like 70% of the time in the long run. And then the alternative would be that he's not getting it right 70% in the long run. Okay, so we've upped the null hypothesis. So now, when I build that null distribution, it would be centered higher. It would be centered up here at pi equals 0.7. It would show us the distribution of sample statistics, the expected sample statistics we would see if it was true that the dog got it right 70% in the long run. We would then again locate our sample statistic that we observed, which was 0.91. And this time that 0.91 would be a little closer to the 0.7 of the center of that distribution. Turns out when we ran this simulation, the p-value we got is 0.0079. So if it's true that the dog gets it right 70% in the long run, then the probability of getting a sample like ours or more extreme is 0.0079. That's still very, very small p-value. And what we really care about is that it is smaller than alpha. So we reject the null hypothesis again. So again, we say, no, it does not seem like the dog's getting it right 70% of the time in the long run either, because we observed a sample statistic that was much higher than that. It's very improbable that we would see a sample statistic like we saw if it were true that the dog were getting it right 70% in the long run. All right, so again, we might say, all right, it's not 20% in the long run. It's not 70% in the long run. What is it? Well, let's up it a little more. So we again do another null hypothesis. This time, let's go ahead and guess that maybe the dog gets it right 80% of the time in the long run. And then the alternative is that he doesn't get it 80% in the long run. We'd build our null distribution. This time the null distribution would be even higher. It would be centered up here at pi equals 0.8. We would locate our sample statistic, p-hat equals 0.91, on that distribution of sample statistics. Probability of getting a sample like ours are more extreme. And it turns out when we ran the simulation that the p-value is 0.13. Now that is actually a pretty big p-value. It is bigger than alpha of 0.05. And remember, when your p-value is bigger than alpha, you will conclude that the null is plausible. So we conclude that it's plausible that this dog is getting it right 80% of the time in the long run. But of course, that doesn't mean that it's true that the dog is getting it right 80% of the time in the long run. It just means that it's plausible. And that was just a guess that we made, remember? We made a guess that it was 20% and said, nah, that's a bad guess. We made a guess that it was 70% and said, nah, that's also a bad guess. But when we made a guess that it's 80%, that seemed like a plausible, good guess. But maybe if I made a guess of 82%, that could also be plausible. Or maybe if I made a guess of 90%, that could also be plausible. In fact, it seems like there could be many, many values that we could hypothesize for the value of pi, and they could all be plausible. What we're talking about here is this idea of an entire interval of values of pi that would be plausible. So we could repeat this hypothesis testing process over and over using different values of pi until we identify the range of null hypothesis values that are plausible versus the range of values that we were rejecting in our null hypothesis. And in fact, it turns out in your book, you'll see that this table is there where they already did this. We did a hypothesis test of pi equals 0.8 and found it to be plausible. The book actually went through and did a hypothesis test where they tested pi equals 0.761 and pi equals 0.762 and pi equals 0.763 and so forth up to pi equals 0.973 and 0.974. And he found all of those values of pi values ranging from 0.761 all the way up to a value of pi equals 0.974, all of those gave p-values greater than 0.05. And so all of those values of pi gave us a conclusion that the null hypothesis is plausible. As soon as they make a null hypothesis that was outside of that range, so like pi equals 0.760 or pi equals 0.759, these were rejected values of pi. And values up here on the other end were also rejected, 0.975, 0.976. They got p-values that were lower than 0.05. So when they hypothesized with a value of pi and got a p-value smaller than 0.05, they would reject. But for this huge interval of values, when they did the hypothesis test, they got p-values that were bigger than 0.05. And so they concluded that each of these values of pi are plausible values for the true population parameter. This interval of plausible values is called a confidence interval. So what we have learned from this table is that it's plausible that the true value of pi is somewhere between 0.761 and 0.974. It's plausible that the dog is getting it right in the long run somewhere between 76.1% of the time and 97.4% of the time. Again, we do not know the true value of pi. We don't know the exact percentage of times that the dog gets it right in the long run. However, our sample statistic is giving us strong evidence that the true long run proportion is somewhere in that interval.